Hello students, in this video we'll construct the metric fundamental tensor. Let's consider a covariant basis. E1, E2, E3. And another basis. E1 tilde, E2 tilde, E3 tilde. Another covariant basis, right? And then what we're going to do is we're going to define Gij to be just EI dot EJ, the dot product of EI and EJ. And this is what's known as the Riemannian metric tensor. This is the Riemannian metric two-covariant tensor. It's a lot of mumbo jumbo. This is what's going to help us measure angles and lengths, okay, in a general setting, all right? And so what are some things to observe about this Riemannian covariant tensor, right? So let's talk about the transformation law first. So what's the transformation law going to be? Well, our transformation law is that EI lower is going to be some matrix over here that's going to be PI lower upper J, EJ, tilde like this, right? If that's the transformation law for the covariant components, then the contravariant components have to transform. There's a tilde, of course. The components in this vector field have to be contravariant, okay? All right, excellent. So that's the transformation law. So if I can plug this in here over here, well, I can conclude. This implies that this is the transformation law. Then I have that Gij is going to be what? It's going to be EIJ, which I'm going to write as PI, and I'm going to put a K over here because I'm using J as an index over here. And then E tilde K, EK tilde. And then that's going to be dot product with what? PJ, it's going to have a PJ, and then put an L over here. And then E tilde L, like that. And so putting these together by commuting these things over here, I'm going to have a PIK, and then a P what? PJL, and then I'm going to have an E tilde K dot E tilde L, and that's going to be what? That's going to be PIK, PJL, like that, and then we're going to have a GKL tilde. So that's our transformation law for this metric tensor over here. So this transformation law proves that this Gij is actually a two-covariant tensor because it satisfies this transformation law, right? In other words, we say that something's a two-covariant tensor if I have this is the transformation law for a one-covariant vector, and if I multiply those things in sequence by each other, so I have a PIK, a PJL, right? So that's a covariant transformation times a covariant transformation with different indices, then I know that that's going to correspond to a covariant 2 tensor, right? So it transforms in the right way, right? And we're going to see exactly that these things in orthogonal and just general with respect to coordinates are exactly just the Jacobian of one transformation with respect to another. Okay, excellent. So that's how it transforms. So indeed, this thing is a two-variant cotensor. And let's see how it works in terms of these so-called musical isomorphisms, right? In other words, how do you raise and lower indices, right? So let's do that. So let's consider a vector V. So a vector V has two representations. It can be covariant components in a contravariant basis, like that. Or it can be what? Or it can be contravariant components, V beta, and then E beta in the covariant basis over here, like so, right? Like either of those representations works. All right, so now what I'm going to do is I'm going to take this first representation over here. So therefore, what this allows me to do is I'm going to take this V alpha, E alpha, like this, and I'm going to dot this with E beta lower. E beta lower, like that. And so what we see by doing this, well, this is going to be delta alpha beta. So this is going to be my coefficient for what? This is going to be my coefficient for V alpha and then delta alpha beta, like that. And so this is going to be my coefficient V beta. So V beta is what we get when we dot with those things over there. Great. So now what I want to do is I want to also be able to write this in terms of the other representation. So V beta is going to be what? Is this representation over here. But V beta is also what? So on one hand, it's equal to this expression over here. On the other hand, I'm going to fill it into this part of the covariant representation. So I'm going to replace this with its contravariant components in covariant basis, right? So this is also going to be equal to what? So also, this is equal to, it's going to be, I'm going to write like this, I'm going to write this as V gamma V gamma like this, and then E gamma lower. Okay, that's a representation of V, right? And this is going to be dot what? Dot, that's my representation, both these are representations for B, dot E beta lower, like this. And so this is going to be V gamma upper, and this is G gamma, and then beta, right? And so what we've proven over here is I've seen how I could take, if I have an index over here, I can lower the index by multiplying by this metric tensor. And so here is our lowering operation. So this is our lowering operation. Okay. What does that tell me? That tells me that if I look at G, and then I have what I'm going to do is I'm going to use the fact also that one thing we failed to mention over here is that this thing is commutative. If I change I and J, nothing changes because the dot product is commutative. So I can also write this as V gamma and then G beta gamma like this. So in other words, we've proven that G beta gamma applied to this upper, this contravariant component V, is the covariant component V beta over here. And so that gives me my lowering operation, okay? We can also define the inverse of this matrix over here. And if I put this, actually I put this into a whole matrix over here, it was called the Gram matrix, okay? And so now what we can also do is we can also do the same trick. So we're going to define G ij upper to be what? To be E I upper with respect to a contravariant component. Now there's no implicit contravariant component over here, but I know that for these things I can look at this, the reciprocal basis, right? Dot what? Dot E upper j like that. So that's the upper. This is a contravariant. This is a 2 contravariant vector. Tensor, not vector of course, it's a tensor. Okay. And now what I'm going to do is the following. So now I'm going to do the same sort of trick over here. I'm going to write, this allows me to write what? This allows me to write a vector V as V alpha, E alpha upper, or as V beta, V E beta lower, like that, okay? Now what I'm going to do is I'm going to actually take this equation over here and dot this part of it with the V beta, right? So I can say, therefore, that if I was to dot this with E beta lower, so V dot E beta lower is the same thing as V alpha, E alpha upper dot what? Dot E beta lower. And that gives me my V beta coefficient like that, okay? So I can dot V with this what? I can do EB dot this representation of the vector in terms of the covariant components. I can also do VB in terms of what? This is also equal to V alpha. Now I can replace this with the contravariant things. I can say V gamma, and then what? And then I want to replace this over here with the what? I want to replace this with an E gamma. So I want to do this the opposite way. So let's do this the opposite way. I want to actually change this a little bit. So let's change this a little bit. Let's do this. I want to do the uppers now. So what I want to do is I want to say, let's look at V, which is going to be V I lower, and then a EI upper, EI upper. And then what I'm going to do is I'm going to hit both sides of this with EJ upper, right? So in other words, this says that if I look at EI upper dot EJ upper, what that's going to give me is that's going to give me a VI, and then GIJ like that, okay? So if I do this VI representation with GJ, I get this representation. Now, I can do the contravariant thing, right? So I can look at now VI, so I can write this vector over here can also be written as, let's write it as VK for example. VK, and then EK lower, that's also, this and this are the same thing because it's just different representations of V in a contravariant basis and a covariant basis. And I'm going to dot this with EJ upper. And what this gives me over here is this is going to give me VK, and then delta Kj, which is Vj. So putting these two things together, what can we conclude from this? We can conclude from this that Vi and then Gij is equal to what? is equal to Vj upper. And what I've done here is I haven't raised the index over here, but I have, and this is equivalent, of course, putting the Vj first, so Vij and then Vi lower is the same thing as Vj upper, and this is the same thing as saying that G with a J and then an I, and then Vi is the same thing as Vj by the fact that this matrix over here is commutative, right? It also is an immediate consequence that these Vij, this Gij upper and this Gij lower are inverse matrices of each other, right? Okay, good. And so this operation is called raising the index, right? So this is the operation called raising the index. In different textbooks, you might see the musical like, so you might call one of these things flat, making it lower, and then you might call this thing the sharp operator, making it sharp, right? So multiplying by the metric or the inverse of the metric over here. Great. And now we're going to, for sure, the same thing about these coefficients. Since these coefficient relationships are true, we immediately get the following relationships too. We immediately get that EI lower is the same thing as Gij and then Ej upper, right? So in other words, if I can lower the index by hitting the this contravariant basis with this thing over here, and then the opposite thing is true over here. I can also say that and if and only if the fact that EI upper is the same as Gij like this, and then Ej lower like so. In other words, these are just inverse relationships of each other by applying the inverse matrix to either side. In other words, what this tells me is that the matrices, if we think of them as matrices, and these are called gram matrices, Gij and Gij are inverses to each other. So in other words, the metric tensor is going to appear all over the place, and so this is the first sort of definition. What we want to do is we want to see that how does it transform with respect to the covariant basis, with respect to the contravariant basis. And so the most fundamental idea is that we need this metric tensor over here, this Gij, because what does it really represent? It really represents telling me how to form the dot product of what? This is going to allow me to compute the dot product of any two vectors in a covariant basis or any two vectors in a contravariant basis using these coefficients. So in other words, now I'm able to do dot products, which allow me to compute angles and lengths in a more general metric, in a more general space sense, other than just Euclidean space and or with respect to orthogonal curvilinear coordinates. We have a more general context for more general coordinates that allows me to compute angles and lengths using this metric tensor. Thank you very much.